Is everybody able to see this whiteboard thing? Yes, sir. Okay, sweet. Yeah, I pulled open the chat. Okay, cool. And it doesn't look like that shows up on screen, so that's good. Sweet. Okay. So Amdahl's law. I guess first off, does anybody know what Amdahl's law even like is or what it describes?
It's supposed to describe like the speed up for whether like when you're using parallel processors as opposed to just like a single processor, right?
Good. Yeah. Right. Exactly. So it describes the speed up factor. Yeah. Like exactly like you said. When we have multiple processors, so that could be either multiple cores, like it's common with computers today. So you might have like a quad core processor, and then the speed up factor might be close to 4. And then there's also examples of like, you have a bunch of computers hooked up on a network and they all do a bunch of processing, and then we could describe the speed up factor for those as well, depending on how many computers you actually have hooked up. So yeah, I think you said that pretty well. Yeah, so let's just think about how we would actually come up with that number then. So let's say we're running one program, and it takes t amount of time to run. And we're running it on one processor. And then we go and we run the same program and let's just say for the sake of the example, I have a quad core CPU and it runs it on all 4 cores, so 4 processors. How much time do you think it's going to take if I have 4 processors, or how much speed up do you think it's going to have? Theoretically.
4T?
Yeah, 4t, or rather t divided by 4. But I think you have the right idea, right? It's going to run 4 times faster, so the time is going to be cut in fourths. Does that make sense?
Sorry, this is a dumb question, but does a computer always run the same program like with the same amount of time every time?
No. There's a lot of factors to that. I don't know if we, and actually that's a fair question. There's a lot of factors that determine it. So if you're running it on a modern computer, you have an operating system, right? So there's a lot of other programs running at the same time. So if I was to run my program that just does whatever, and I have Chrome open, and I have Steam open, and I have Discord open, and I just open a million processes, the thing is, all of those programs have to be running, right? So they each need to get processor time. So your program is going to get a little bit less processor time the more things that are running on the system, on top of some other factors, including the fact that those programs are also taking up memory that might be using, and caching issues that we'll get into later. So yeah, the time isn't always going to be consistent, and that's not because of your program, because that's deterministic. That always does the same steps every time, right? But rather because of the physical limitations of the computer, if that makes sense. Any other questions on that, I guess? Or hopefully that cleared it up. But t over 4 is true if the work is divided into 4 equal parts, right? Yeah, exactly. So that's just theoretical, and we'll get into why that's not actually necessarily true, and then relating it to Amdahl's law. But yeah, you're right. Yeah, does everybody get why it's t over 4? Since the time's just going to get cut into 4 equal parts, theoretically, assuming that the program just is perfectly dividable. So time. Yep. Cool. So let's just say, to more generalize it, I run the same program. Ooh. Oh no. I hit a thing on the pen. Hopefully that just... Okay, cool. Just open a new page. Same program, and let's say we're running it on n processors. Lost me is Bryson for attendance reasons. Oh yeah, actually, thank you for reminding me. Make sure you post in the chat for attendance reasons, because Dr. Fonseca has a script that reads the chat and then takes attendance for everybody. I think that's how he grades this. Yeah, but so if I had the same program running on n processors, how much time do you think it's going to take to run?
T over n.
Yeah, exactly, right. Theoretically, it'll take t over n time. Cool. So the speed up on these, so this one might not be obvious, but what's the speed up if I just run the program and compare it to itself?
0.
Or actually 1.
1?
Yeah, 1. So it'd be, I guess we're defining it as like a multiplier rather than a percent. So it'd be like a 0% speed up, but we normally do it as a number. So, right, although we guess frame it a little bit differently. Yeah, so this one's 1 times faster. So how much would the 4 processors be then? Be 4 times, right? And then obviously this one would be n times faster, right? Okay, so let's just open a new page here. So let's say we want to figure out how much speed up we're going to get with a process or a program. So if we wanted to do a speed up factor, normally what we do is we take the amount of time that it takes for the original to run, and then we divide it by the time it takes the sped up version to run. Right? Because if I had it running 4 seconds at first and then I run it again and it's 2 seconds, then you would say the program's running 2 times faster, right? So let's just take a second. I probably should have made some more room for that. Let me erase this example really quick. Hopefully that made sense. That's like, okay, cool. Yeah. So we'll go back to like the previous example in which we say that the program takes t amount of time to run. So that's a hard t right there. And then we need to talk about the speed of the parallel version of it. So like somebody mentioned earlier, that perfect 4t or n divided by t, t divided by 4 speed up or amount of time is going to be dependent on the program being perfectly parallelizable, which is not realistic. Not everything is going to be able to be run perfectly divided across all the processors. You might have some things that have to wait for each other or just can't be done in parallel. So what we're going to do is we're just going to describe that as a fraction. So we'll say that f amount can be parallelized. So that's just some decimal between 0 and 1. Parallelized between 0 and 1. What are things that can't be parallelized? So one example that comes to mind, because I took a class on this, was networking. So let's say I have a network. Let me just open up a new page really quick and then we'll come back. Let's say I have a network where like each of these circles is a computer. And it's like this maybe, and then there's that. So only things that are connected with a wire can actually send each other messages or like program data, let's just say. So let's say, you're computing an average and these can only send numbers between each computer. So this is like 0, 1, 2, 3. So 0 can only send to 1, 1 can send to 2, and vice versa. They can go back both ways. 0 can send to 2, but 2 is the only one that can reach 3. This can't necessarily be parallelized perfectly because these guys have to wait on processing from 3. So they can compute at the same time. That's the parallelization part. But they might, for the final part, have to wait for 3 to send back the stuff. So there's networking problems. There's some problems where even if you're on the same computer and share the same memory space, like the same RAM, you might have to wait. I don't know if I can explain any of those super well without going into a lot of detail. If you're interested, I think it's called the Dining Philosophers is a really common example. Or like the smoking problem, I know, is another one. I remember the Dining Philosophers, but it would take a while to explain. But yeah, there are definitely ones. I suppose recursive functions can't be parallelized. No, those can, because a recursive function is just a function calling itself. I don't know how much you guys have done with threads, but each thread has its own stack that it can use to call recursive functions. I hope that answered everybody's questions. And there's probably a better example of that than the network one I gave, but there are definitely problems where you're stuck waiting for some portion of time. Actually, I guess one easy example would be an average. So an average, right, we'll just go back to the other page. An average, you add like all the numbers up together, ... plus n sub I, and then you divide by the amount of numbers that there are. So what I can do for parallelizing that is I can give, let's just say, processor 1 a couple numbers, processor 2 a couple numbers, processor 3 a couple numbers, and let them all add up. But the last step, the dividing by I, they can't all just do that by themselves, right? I mean, actually, I guess they could. But let's just say, we're waiting for the sum to finish, and we don't necessarily know the count of all these beforehand. We might have to wait for them to all count it, and then one processor has to do the division by I. So that last division by I wasn't parallelized. They had to wait for it. I think that would be a simple example, but most of that would be parallelizable. But anyways, I guess I digress. Back to this. So let's get back to this. So let's say the time it takes for a program to run on one processor, or the time of the original, is just t seconds. So what we're going to do is we're going to say that f is the fraction of the program that can be parallelized, and then the rest of it has to run sequentially on one processor. So then, if f is the amount of fraction that can be parallelized, then we know that f is going to be multiplied by the time it takes to run that parallel process. So if I have n processors, how much time, based off of what we did earlier, how much time do you think it's going to take relating to t if we have n processor? How much time is that going to take? If anybody has a guess. I know we digressed a bit, so it might be hard to remember. T over n, yeah, awesome. Good job, thank you. So it's going to take t divided by n, right? Because we're going to take the time and split it into n equal parts. And like you do with averages, right? You just multiply it by the fraction, and then we add the other fractional part of it. So if f% of it can be parallelized, what percent can't be parallelized? 1 minus f, right? Yeah, that's what you said. And the reason that is, right, is just that if this is like, let's just say 60%, then this would have to be 40%, right? Because they always have to add up to 1, and it'll always be 1 minus the fraction. Hopefully that's clear. And then the amount of time that it would take the program to run by itself, since this is I guess I should probably highlight this. This is the parallel part. How do you find f? It depends on your program. So you would want to actually look at all of your lines of code and figure out, hey, this takes this many steps compared to the total steps of my program. So let's just say I have 2 instructions that can't be parallelized out of 100 instructions, then I have 2% sequential and 98% parallel. So it's kind of up to you, the programmer, to figure it out. And then hopefully it's clear that the sequential version takes t seconds to run. Does anybody have any questions on that so far? We'll simplify this in a second, but that's just the general derivation. Okay, so let's go really quick. Oh no, I want to make that to go back up. Oh no. Makes more sense in the book. Okay, that's good to hear. I do think they wrote it a little bit strange. I was looking at it earlier. So, okay. So let's just rewrite that really quick. So we said it was t over f. Actually, I guess I should write it the way the book writes it. So they write the sequential first and then the parallel. Yeah, did the book even define it? It did. I'd have to look up the page. I think it's in chapter 2 somewhere. I have 3 versions of the book, so I'm not completely clear, but I think it's in chapter 2. Oh yeah, but they wrote the parallel version first, so that would be 1 minus f. In fact, they probably wrote f as the fraction that can be sequential, but know that you can flip them, really, right? In the 10th edition, it's 2.3. That's probably where I saw it. T plus, and then we said that there was a fractional part, again, the parallel version, times t over n. 2.3 and 11th, good? Okay, cool. So it's the same, it looks like. All right, so does anybody see anything in this that looks like it can be simplified at all? There's only really one thing we're going to do.
Did you factor out the t?
Yeah, exactly, right. So is it okay if I just cancel all the t's across all of these? Hopefully that makes sense. So we get 1 over 1 minus f plus f over n. And then that's probably good enough. So we'll say that's good for our Amdahl's law. And then we'll probably just talk about one more thing. Anybody have any questions on that, or seem okay? Okay, yeah. Okay, fair enough. This makes a lot more sense. Good to hear. So do I have another page? Okay, cool. So let's do one last thing. Actually, let's just reuse that. Can I just copy and paste things in this program? Add a new page. Oh, awesome. I guess I can't erase it though. Oh well, that's fine. So let's consider one thing. So let's consider an example, really quick, where f equals 0.6, so 60% of the code can be parallelized. And then we just have some arbitrary number of processors. So then we know we're going to get 1 over 1 minus 0.6 plus 0.6 over n speed up. And then if we just simplify that really quick, we get 1 over 1 minus 0.6 is 0.4. Plus 0.6 over n, and then yeah, we'll leave it like that for now. So what I want to do is I want to consider what happens when I throw more processors at things. So I could buy a quad-core computer, I could buy an 8-core computer, I could buy a 12-core computer, I could buy a computer with 100 cores. At some point, you're kind of just spending money for the sake of spending money, and it doesn't really do much. So does anybody have a suggestion as to how we could figure out like a maximum amount of speed up that we could get, maybe using some calculus? Awesome, yeah. Oh, yeah, sorry, what you were going to say. Alright, that's okay. Yeah, so like, I see a bunch of people saying limit, and sorry for whoever I interrupted. Yeah. So let's take this, and let's take the limit as n approaches infinity. That is, the processors we have approaching infinity. What is this going to turn into if I take the limit as n approaches infinity?
0.
Right. So this will be 1 plus 0.4 plus 0, which is 1 divided by 0.4. And this is what, 2/5? So that would be 5 over 2, which is 2.5. So if I have an example where 60% of my code can be parallelized, the most amount of speed up I expect to get, no matter what computer I run it on, is 2.5. I don't expect to get any more after that. So if you notice you're getting a speed up of like 2.4 with 8 processors, then you don't really have a whole lot of a reason to go and buy 16 processors because it's a lot of money, and you know, you can get the same amount of speed up. Any questions on that? I think that's probably what we'll settle on for Amdahl's law. So, anybody have any other questions regarding material this week or out of the book? Otherwise, we can just start doing some problems that I picked out.
I don't fully understand what F is, actually.
Oh, okay. Yeah, so F is the percentage of your program that can be parallelized. So
in this case, is 60%?
Yeah, so I just picked 60%, but you would have to find it on your own depending on the program you wrote.
I see.
Does that make sense?
So what happens when F goes up or down?
So if F goes up, that would mean that more of your program is parallelized, right? So if I'm able to run more of my code on parallel processors, do you think the speed up would go up or down?
Up.
Up, right? Because the more I parallelize it, the faster it should run. And then vice versa. If I can't parallelize a whole lot of it, I expect the speed up to go down, right?
Yeah. Okay, I think it makes sense now.
For sure. And let me know if you have any other questions. F is provided for this course then, right? A higher F correlates to more performance from more processors. Right, exactly, yeah. So F is variable. Do you have a code example? Probably. I'd have to look. I don't think I'll look right now, but I probably have something written from when I took parallel processing. I might post that in the Discord if you're interested. Like parallel multiplication, I do have exactly that, actually. I don't have the computation for Amdahl's law for it. Maybe. It might be in a report somewhere. Yeah. 2.5 isn't a until it means 2.5. A unit until it means... Oh, yeah, it means... Yes, this is speed up factor. So we're comparing a sequential version of a program versus a parallel program. Yeah, they usually have you do one threading program in assembly. Did you count the lines inside the critical zone as the parallel steps? Yes. Generally. Although you might not necessarily have a critical zone, you might just have something that's parallelized. Because a critical zone just means that... you'll have to forgive me, I don't remember the formal definition, but it's something along the lines of things that have to be waited for to finish and that can't share the same memory resources, and I think you're really only limited to that if you're running it on threads, which share the same memory space. Yeah, and race conditions might actually lead to that. Actually, that's one last thing I guess we should leave with. So this describes a theoretical speed up, but like somebody asked earlier, do you always get the same speed up every time you run a program? You might not, because you might face things like race conditions. You might have resource problems. You might have bus contention. There's a lot of physical things that might actually affect the speed up. So even though I got theoretical for this program that runs 0.6 parallel code, I might get a really slow speed up factor if there's system factors that actually affect it. F could be variable. Yeah, F is a variable. It depends on your program. It's a constant for your individual program, but it's a variable in the context of Amdahl's law. Okay, yeah. Any other questions about Amdahl's law or anything else from lecture? Okay. So, if not, I think we'll just start working on some of the problems. So, man, I want to stop selecting that. I think Amdahl's law is probably the most important thing in this class, so I kind of wanted to go out of my way to go over it, and I know Dr. Fonseca mentioned it along with Little's law. I have an example of Little's law later, if we have time. Okay. So... here's just a quick little example, because I think this can be a little bit confusing at first. So let's say, and we're only going to do A, B was a little bit in depth. So if you want to go try that on your own, that's fine by me. We're going to write a program on the IAS Instruction Set, which is just this machine here in the textbook, that computes the sum from 1 to n, basically. So it just does like 1 plus 2 plus 3 plus 4 until we hit some number n. So we assume the computation does not result in an arithmetic overflow, and that x, y, and n are positive integers. And it says IAS did not have an assembly language, but we're just going to pretend it did for a second before we get the actual answer. So if you remember, the way you can take the sum of integers, if you've taken discrete math, is like 1 plus 2 plus 3 plus 4 up to n is equal to n times n plus 1 divided by 2 as a shortcut. So let's just try to evaluate this algebraic expression. And so what we have access to here is some opcode. So if you remember from assembly 218 that you had like an instruction like add, load, store, jump, that kind of thing. We have all that right here for the IAS. And then it says it was machine code, which just means rather than writing add, load, whatever, you would just write the corresponding opcode in binary. So like load would be that instead, but it would be basically the same program. So if I wanted to evaluate this expression, I think the book did a pretty misleading job here because I looked at the answer key. Is there anything anybody thinks we should do first? One line of code, one instruction. Yeah. So the processor can only do one instruction per core at a time. Ignoring pipelining, that is. So if I want to, and sorry if this is kind of hard to see, let me write it a little bit bigger. So if I want to evaluate n times n plus 1 divided by 2, what do I have to do first in assembly? First load into memory. Okay, awesome. Somebody picked up on that. I totally didn't even think about that when I was looking at it, but you guys are on top of it. So yeah, let's just make some memory over here. Do it green because RAM is green. I'll just say memory and then the value. So let's just have some arbitrary things here. So I'm going to do this a little bit differently just for the sake of making it fit on this page. Just know on the IAS machine it's 32-bit, so these would be a lot longer memory addresses than I'm actually writing out. N plus 1 needs to be evaluated first, right? Yeah. So the numbers we're going to need in memory are n, 1, and 2, right? Does it have labels like x86? I guess so. It would be a memory address more than a label. If it has just machine code, it doesn't have the convenience of having like an actual assembler that gives you a label. Do we have access to the amount of numbers, or do we have to count them? Yeah. You're going to be given it in advance to that question earlier. So let's just say that's n. It's been loaded into memory. It's like read into by the user via like argv or something, and then it gets stored in this memory address. Yeah. So everybody's saying we need to load first, right? So for the assembly, let's just move over a little bit. Okay, that's fine, I guess. So the first thing we need to do, oh, sorry to interrupt you, but are the assessments tests based on the back of the book questions? I have no idea. You'd have to ask Dr. Fonseca. Load into another address. Yeah. Actually, I guess I should have explained a little bit more. Yeah, so somebody's saying take the n plus 1. I saw some other people say that earlier. Yeah, so let's evaluate n plus 1 first. And then one other thing I guess I should clarify. I probably explained it in 218, but we have a register called an accumulator, and they just call it AC here. And that, let's just zoom in a little bit. Maybe I can fit more stuff. AC is where all of the things that need to be operated on are going to be stored. So I know on like x86 you have to store things in RAX, I think, right, in order to do multiplication at least. Accumulator is similar to that. It stores the results of operations, all this stuff, and it also needs to have one of the two operators for add. So what we want to do first, somebody was saying, was load n plus 1. So we need to calculate n plus 1. So the first thing we'll probably want to do is just load n. And actually, we're not going to write it like that. Again, I should probably, I guess I do need to zoom out. Hope that's not too hard to see. we need to load a memory address, right? So rather than load n, since it's a variable and it's in memory, we're going to need to load m of x. So what we're going to do is load m hex 0, and that'll just load n. And then what else should we do? So somebody was saying like n plus 1, right? So the next thing we'll have to do is we'll have to add n, which we've just stored in the accumulator, by 1, which is at memory address hex 1. So is that clear so far that this puts n into the accumulator and then this adds 1 to it, and then n plus 1 gets stored in the accumulator? And do you mean m? Oh, so m, referring to this symbolic representation, so I'm doing like the assembly equivalent, the memory address. So like this right here is loading the variable stored in memory at address 0, which is n. So this memory address corresponding to that one, if that makes sense. Because I guess when you're dealing with memory, you can't actually get the value of it itself. You have to load it from memory with the address. So the next thing we probably want to do is multiply by that n, right? So does anybody have any suggestions based off of these? Yeah, awesome. Multiply by memory address hex 0, 0, which again is n at that memory address. Cool. So this did n plus 1 times n, and then the last thing we got to do is then divide, right? By memory address 2, like somebody said. Divide by memory address 2. All right, and then we're done. And then we could move the memory stored in the accumulator into a final variable, I guess, just for a return point, which is what they have in the book. But I think this is fine for now. So any questions on that before I move on to the last part of this? Does it make sense how I got this part up at the top from this code? Yeah, make like sum of y equal to the accumulator, right? AC with or the memory at address hex 0 was loaded into the accumulator. The accumulator is part of the processor, so it's an actual register. It says multiply mx by mq. Does it multiplies by you're right. Yeah, wow, that's unfortunate. So yeah, I guess good catch. What is MQ? Is MQ on the table just referring to any register? So it's referring to a specific register. Whenever you see these capitals over here, I guess there's only a few of them. It's on one page in the book earlier in the chapter. They have all the registers listed out. Yeah, so somebody actually had a good point. So I should have done something here. Let me see if I can move it down. MQ is like the accumulator. It's specifically for this machine. I hope I can move this down. Load MQ MX. Yeah, add to current page. Good enough, I guess. You have to store m of x first. Yeah, so let's just go over that one more time. This eraser is way too small. So again, let's just refresh where we were. So one thing I should explain first is that, let's use blue, AC and MQ are basically the same in terms of what they do. These are just two registers in the CPU that sit there and they hold values, and then the ALU operates on whatever's inside of these. So the only difference between these is that apparently this specific register, and this is exclusive to this architecture, this IAS that the book describes, needs things to be in MQ before it multiplies them. you have to store m of x first. Yeah, so load m of x, just to review what we did here. We wanted to evaluate n times n plus 1 divided by 2, so we first loaded n, which was at memory address 0, into the accumulator. And again, these only take one operation or operand, so this loads that, and it just assumes it's the accumulator. We added 1 to it, and then we're going to have to do the load MQ part here. Like somebody pointed out earlier, yeah, I made that mistake. The multiplication only works on the MQ, put most significant bits of result in an AC, which I guess is what we care about. So it needs to be loaded into the multiplier quotient register, I think is what this was called in the book. Again, it's specific to this architecture, so it might not be a thing in x86. Instruction set must be ancient. Yeah, I think it said it was from like the 70s or 80s in the book. But does that make sense why we have to do this first? Somebody pointed out in the chat. But load MQ puts the contents of MQ into AC. Oh, did I have that backwards again? Transfer contents of register M. Oh my gosh. Transfer MX to the transfer constant. And thank you for pointing that out. I messed that up again. Transfer contents of accumulate to memory. Oh wow, yeah, we'd have to go through a separate thing, right? So yeah, store and load. Yeah, dang, we have to do that, huh? MQ to the accumulator. I guess I should have read this more in depth. Yeah, we'd actually have to go and create a variable. Alright, hopefully last time I have to do this. Otherwise we'll just get n, not n plus 1. Or I think it would override the contents of AC with whatever garbage is in MQ. Yeah, I'm sorry. Let me erase that. Alright, let's add current page. Hopefully it lets me erase this. Aww. Store MX, yeah. I don't think I can do a white color, can I? Can I just throw this? Yeah, let's just... Like in computer, we'll just do a lazy delete. Just throw that over there. It's good enough. Oh well. Yeah, okay. So somebody... I think a couple people in the chat are saying the right thing there. So, yeah, sorry. This is... n is in AC. This is n plus 1 is in AC. We can't move directly from the AC to the MQ register, apparently. So we need to go through a memory address first. So let's just make some memory address with, whatever garbage in it. So we'll store probably. Store transfer constants of accumulator to memory address X. So we will store the accumulator in the address that we're just going to allocate, which is 3, and then we can move it to the accumulator, or sorry, the MQ that somebody pointed out. That one takes 2, although the name might just be load MQ. Memory address 3. Hopefully that's all actually correct now. And then again, we would probably store this in some memory address when we're done, but just to keep it simple. Alright. Do I have it all right now? Did I screw up again? Alright. I'm not... Oh, actually, would MQ work in moving n into MQ and retaining? MQ hex 0? Yes, actually. I wish I would have read that earlier. And then we could have just multiplied them. That would have been a lot easier. Oh well. I for the sake of time, I'm not going to rewrite it again. But yeah, you're right. That's a lot more efficient. Loading it into, or just loading this straight into MQ because we're going to multiply it by this anyways. That would have been a way better idea than what I did. All right. So now let's finish this. So it said earlier that there's not actually, how do I move this? Oh, there we go. There's not actually a assembly language on IAS. So let's try to move this if it would let me. Let's try to turn this into the actual way we would have programmed it on that machine, and then we'll say that we're probably good. Okay, so this part should be pretty easy. Again, consider that this I'm only going to write as, what, 2 bytes? But it would be 4 bytes in reality. So this memory address would be 3 bytes instead of the 1 byte that I have, which I was just writing so I could fit it on the screen. So load memory address whatever is this opcode, no, this opcode right here, this one. So it's 000000001, and then I think that's just a squiggly. I think it's just 1. So the actual program would be 0 0 0 0 0 1 2 3 4 5 6 7 1. So this is the opcode part, and then it would be memory address 0. So 0 0 0 0 0, and then 3 more, 0 0 0. So that's this translated into opcode, and again, I'm only doing it as 16 bits rather than 32. So there'd be 16 zeros in between this that I'm just not writing. We'll just pretend it's there. By any chance, could you post the notes after class? I will try to, and this is going to be recorded too, so if you need to go back and look at it, it will be there. Cool. So we have the next one, which is just add. So add memory address 0 is right here, and that is the opcode, which is 0 0 0 0 0 1 1 1. So that's the opcode part. And then this is the operand. I'm writing in colors, but these are conjoined. Realistically, it would just be one 32-bit bit string. And then the memory address is 0 0 0 0 0 0 1 2 3 4 5 6 7 8. It might end up on Dr. Fonseca's YouTube. I'm not really sure what he wants me to do with it. He just told me to record it, so I'm doing it. And then hopefully everybody's getting the idea. Do you want me to keep going, or? Yeah, like and subscribe, y'all. Does everybody get the idea, or do you want me to finish it? No, we're good? Okay. Everybody else makes sense? Okay, cool. I don't want to write all that out. Alright. So let's take a look at the next one, I guess. Again, unless anybody has any other questions that they want to work through first. Because I only have 2 more. Oh, we don't have that much more time, I guess. So this one was actually not too bad. Okay. So we have a benchmark program is running on a 40 megahertz processor. The executed program consists of 100,000 instruction executions with the following instruction mix and clock cycle count. So whenever it does an integer operation, that takes 1 clock cycle. Whenever it does a data transfer, that takes 2 clock cycles to happen. If it does a floating point thing, it takes 2 cycles, and some sort of transfer, it takes 2. So we want to figure out how many clock cycles does it take for the average instruction. So we want to determine the effective CPI, MIPS, and execution time for this program. We can't really do execution time without having the actual program. I think that was a weird part of the book where they didn't actually mention what the program was. So let's just ignore that. So let's do the CPI and the MIPS. So does anybody have any suggestions on how we can figure out the cycles per instruction for this one? It says it right there. Kind of. I mean, we have to use this information for it. I'll give a couple seconds, because if somebody's writing out the answer, it is probably going to be really, really long. It's effective CPI or ratio. Oh, I guess the effective part isn't too important. Yeah, it's a ratio of cycles per instruction. All divided by 100,000. Yeah, weighted average. Yep. Okay, so 2 people have it there. CPI is cycles per instruction. So we need to take a weighted average, or alternatively we could divide it by 1,000. I'm probably going to do the weighted average part, but this would also work. So if we have 100,000 instructions and 45,000 of them are integer, then does it make sense that 45% of the operations are integer operations? 1, 0.5, 0.32. Yeah, that's exactly right. So like saying there, yeah, we're going to take 0.45. So there's 45% of the instructions are integer instructions, and those take 1 clock cycle each. 32% of the instructions are data transfer, which take 2. And then 15% take 2, which are the floating point ones. And then last we have 8,000 out of 100,000, so 0.08 take 2. Is that clear where I got all of those from? And somebody said it in the chat earlier too. Alright, I'm gonna assume everybody gets where I got those from. Basically, I just took those and divided it by the 100,000, right? Hertz is defined as 1 cycle per second. Yes, so we couldn't determine the execution time based off of that. Of one one instruction, I suppose we could, but if it's an entire program, then we would kind of need to know what instructions it has, like how many are integers and how many are data transfer and floating point and all that. So they'd have to give us more information. But we can determine how many millions of instructions. So this is to calculate the average CPI. Yep. Yeah, the amount of cycles that we expect per instruction. In fact, they probably should have put average here, but yeah, you're right, it's the average. I think this works out to be something like 1.55. I could pull open a calculator, but I did this earlier. Let's just cheat a little bit, open up the answer key. Where it's not going to open. Yeah, 1.55. Okay, I'm going to take your word for it. I think that's what it was earlier. So this has 1.55 CPI. Sorry, I might have missed this, but why did he cross out execution time? We're just going to skip that, because they didn't give us the information, I don't think. I think it's somewhere in the book, and I couldn't find it. So I'm just going to skip it. Okay. So last thing we'll do is let's determine the MIPS. So does anybody have any suggestions on how we can take the CPI and turn it into MIPS, given we have some other information up there? CPI times megahertz. I think you're right. Cycles per instruction. That would be cycles per second. You're almost right. You're on the right track at least. So let's just do some of that fancy high school, whatever it's called, dimensional analysis. 1.55 cycles per instruction. Yeah, somebody said it there. Almost, actually. Not 40 divided by 1.55, but pretty close. Megahertz divided by, yeah. And you'll notice I'm going to have it flipped here, but I'm going to at least justify how I would come up with this answer if I wasn't just memorizing it out of the textbook. So does it make sense? Cycles per instruction as a fraction would be cycles over instruction. We have that the processor is running at a clock speed of 40 megahertz. So we need to convert that to hertz. And like somebody said earlier, hertz is like an inverse second. So when we're talking about processors, a hertz is a, let's see, cycles per second. Oh yeah, and so I guess I should have clarified that. MIPS stands for millions of instructions per second. So what we want to do is get to a unit that says instructions over seconds. What you'll notice is why my thinking here is a little bit flipped. I have this on the bottom. So if we want this to be cycles over second, and we want seconds and instructions in the final answer, we know seconds are going to be up here, and cycles would have to be at the bottom. So the megahertz is going to have to be down here, which would be 40 times mega is 10 to the 6th hertz every second. Does that make sense how I came up with this, I guess, first? And then everybody is right in the chat saying that it should be the other way around. I just have it upside down. We can fix that. I guess the last thing would be, the reason I did that is these cancel, right? We get 1.55 over 40 times 10 to the 6th. Seconds on top, instructions on bottom. Seconds per instruction. So if we wanted to figure out instructions per second, we would flip-flop that, right? So it'd be 40 times 10 to the 6th instructions per 1.55 seconds. And then that works out to some number. And then alternatively, just if you want the easy thing for the test, like everybody was saying, take the hertz and just divide it by the CPI. That'll work. I guess I was just justifying how I would work it out if I didn't remember that. Cool. I hope that one was pretty straightforward. Anybody have any questions on it before I move on to the next one? Oh yeah, sorry. And then MIPS. So we divide by 1,000,000. Yeah. Well, actually, other way around. You take a lot. Oh yeah, actually, sorry. Yeah. Never mind. Last thing. Yeah, we would take whatever this number is and then divide it by 1,000,000 because we want 1,000,000 instructions per second. I'm sorry. I had instructions per second. So, yeah, good catch. Thank you. And then divide it by 1,000,000, which is 10 to the 9th, right? No, 10 to the 6th. Oh, awesome. That is good. Maybe we can work this out. 1,000,000. Yeah, we would do that. And then these cancel, and we get 40 divided by 1.55. Which is probably roughly like, what? 30 something? 37? I don't remember, and the answer key's not opening. 25.8? Okay, maybe I shot a little high. 25.8, thank you. MIPS. And then that's our final answer. So thank you, whoever caught the fact that I forgot to divide by 1,000,000. Because it's 1,000,000 of instructions per second, and I only had instructions per second. Okay. Any other questions on that? Nope. Okay. If anybody has any questions, let me know. Oh yeah, sorry. Go on.
I thought the instructions in section per second would be higher because multiple instructions are being. Oh no, I get it.
Oh yeah. Why it would be between like 1 and 2?
Yeah, I see now. Because the cycles, it takes longer per instruction, right? Because it takes 2 cycles.
Yeah, for these ones, which make up roughly like 55% of the instructions for this architecture.
Alright, I get it now.
Sure. Okay. If we don't have any other questions, I think we'll just move on to the last one. I think we only have like 10 minutes left anyways, so let's try to blaze through that. Oh, this is in the way of the screen though. Okay, new page. Alright, so we have one last one, which is Little's. Oh, I guess I have 2. Would you guys rather do Little's Law or just means? Up to you. I have 2. And by means, I mean like arithmetic, geometric, harmonic. Which is more relevant to class? General definition, then examples of means. Which fits in 10 minutes better. I mean, I can explain a mean pretty easily, but I also think everybody can probably work it out on their own. I mean, everybody knows how to take an arithmetic mean. And let's just do the means. The arithmetic mean is really easy. And we have... Oh, is it 1250, not 1230? Oh, you're right. You're right. Never mind. We're doing both. Thank you. I forgot. This is an hour and a half class. Okay. Well, let's just do the means first. It's pretty easy. It won't take that long. Do I even need to go over arithmetic mean? I hope everybody knows how to take that. It's just an average, right? I'm hoping we'll skip that. Means we could skim the chapter. Okay, fair enough. I mean, means I guess are more useful if you're gonna like write a paper. It might be useful to know these 2. You've probably learned these 2 in like high school. I mean, you only really use that one. Actually, this is a good opportunity for me to explain why they do this weird stuff too. Okay, so an arithmetic mean is just you take all the numbers, you add them together, and you divide by how many numbers you have. I hope that's clear. I'm just going to skip it. A geometric mean is basically the same thing. So if I had numbers x1, x2, x3, x4, ... x sub n, then in order to take a geometric mean, rather than add them all up and then divide by the number I have, what I do for a geometric is x1 times x2 times x3 ... times x sub n. Oops. And then I take it by the nth root. So it's almost like an arithmetic mean, it's just with multiplication and square roots, or not square roots, roots instead. And the reason you would do this as opposed to that, does anybody actually know before I say it? Why would you use a geometric mean over an arithmetic mean?
Isn't it like less biased than arithmetic mean can be with like outliers?
Right, yep, exactly. Thank you. So it's less sensitive to outliers. So if I have like a really huge number, it doesn't skew the data as much on this one as it does with that one. So if you think you're going to measure the runtime of your processor and you have one where the runtime was just ridiculous because let's just say you're running in on Bobby and everybody else is trying to run their program at the same time, your program's probably going to run a lot slower, and so you might just get one random outlier. So if you're like measuring it for a report or something, you might just want to use geometric mean. Yeah, so awesome. Whoever said that. Cool. And I guess the last thing, I hope you guys can see it. Why do they do this? Does anybody know why you would write it like this instead of just multiplying it? This like seems like a lot of work. Taking a natural log, that's hard. Power of E. And I'll give you a hint, it has to do with computers. You wouldn't do this by hand. It looks messy? No, it's not. Not human error. It does have to do with computers. There is a logical reason as to why we do this. I'll give you a hint. If you notice here, this is a summation, which is addition, and this is pi, which is multiplication. What happens when you multiply numbers in a computer versus when you add numbers in a computer? If there's a lot of numbers, what do you think is going to happen? Multiply is faster. It is, although I guess that would be more of an incentive to do this reason than that reason.
I think it's because multiply can overflow.
Awesome. Yeah, you're right. So multiplication has overflow more easily than this addition does. So if I was to multiply 0.2 times 10 to the negative 20th times 0.3, I guess in scientific notation it'd probably be like 2 and 3, but times 10 to the negative 100th. I guess in this case it's underflow, but you have the right idea. If you remember, like that IEEE 32-bit representation, if it's a float, it's 2 to the negative, what? There's like 7 bits, I think, for the first part. So it's like 2 to the negative 25th. This is going to be way too small to fit in a register correctly. You're going to lose a whole bunch of precision, and you're going to end up getting the wrong answer if you multiply something like that. So yeah, whoever said that was totally right. We get overflow. So this is why you would use this one. If you take natural log and then just add it, you're going to get the same answer, because if you remember your algebra, e to the ln cancels out, but we get an answer that actually fits in registers. Alright, so I think the last one, I'm not going to go too far in depth on it, it's almost the same sort of thing, is harmonic. So the reason we use this one is essentially the same as the reason we use that. It's a little bit less sensitive to outliers than a arithmetic mean. So it's really almost just this, but upside down. So if I had x of 1, x of 2, x of 3, what I do is I just take the amount of numbers, that goes on top instead, and then we just do 1 over the first number plus 1 over the second number plus 1 over the third number. I don't have a whole lot to say about that. I don't see anybody really use harmonic mean very often, at least in computer science. I'm not sure. Maybe it has other applications. But that's at least how you take it. Any questions on that, or seem pretty straightforward? I think the overflow one was probably the most important part here for CS. Especially if you do machine learning. What's a harmonic for? It's just another way to represent a mean. So a mean is just like a way to measure. I'm not sure if average is the great way to phrase it, but like the middle timing, like the I guess kind of what you expect for your whatever number. Like practically, I mean, same practical applications as these ones, I guess. You know, if I was to come up with some algorithm and I wasn't describing it using time complexity, because maybe it was trying to solve like an NP hard problem or something, you know, I would probably measure how fast the program runs on a machine, and then I would just demonstrate, oh, this is the average, and then just use one of these 3. Measuring execution rate. Yeah, exactly. So the time that it takes for your program to run. And it's more useful when something is not algorithmic, or I guess that's a bad way to phrase it. It might be, I know not everybody has discussed like NP versus NP complete and all that stuff. When you have a problem that's really, really hard to solve, and you might not be able to mathematically, I don't know if everybody's taken 302, but like show that the O of n is like a polynomial, you might want to show the runtime instead of the time complexity to demonstrate that your idea is better, or your algorithm's good. Okay, so let's move on to the last one, and I guess we'll just call it unless anybody has any questions. And sorry in advance, the graphs are really, really small here. I couldn't find it anywhere bigger in the book. They were all just super small. So again, we'll just ignore B, because it's really just the same thing, I think. Determine the area of the 10 rectangles. And oh wait, 1, 2, 3, 4, 5. No, let's just do this one. There's another image on a different page. Let's just do this one. So we have these 6 rectangles, 1, 2, 3, 4, 5, 6, and they're actually just these numbers up here described by that. So in figure 2.8, which is that one, I guess of these 3, we have jobs arriving at t equals 0, 1, 1.5, 3.25, 5.5, and 7.5, and each of those jobs complete at those numbers. So we have essentially like small snippets of code coming into the processor. They get allocated to a core, and then they run from this time to that time, and then they finish. So what we want to do is, this is actually an example of Little's Law. We want to discuss how many of these are in the system at a given time, and then determine the area of the 6 rectangles. Will probably help us. So Little's Law was lambda times W equals, I think it was capital L. Actually, I have to double check that. That's right. Okay, cool. Thank you. And it measures the average number of jobs you have in a system at a given time. And we'll talk about why that's important briefly. So Little's Law is chapter 2.3. I just want to make sure I have the variables like assigned to the correct thing too. Yeah, lambda W. I think lambda was like the average time, right? For the average time that W is in the system. Oh, let's find the average number of items. I think I have that backwards. Oh, okay. Yeah, sorry. Lambda is items per unit. Okay, thank you. Is average items that arrive per time, and then W was, yeah, the items stay in the system, and average is the average time that an item is in the system. So again, you'll hopefully notice that if we were to multiply these out, the units would cancel. This T is the same as that T in terms of units, and then we just get average items. Okay. So we would need to figure out the average items arriving per some amount of time, and then the average time an item is in the system. So this part actually only describes W, I believe. So they say take the area of the 6 rectangles. I think that's a strange way to phrase it. What they really mean is figure out how long everything is in the system for. So the length here is just, so if we were to zoom in on this, this is like 0, that's 2, this right here is the 1, and then this is like 3. So like the start of this rectangle is when it arrives in the system, and this is when it gets out of it. So we just have some sort of queue for running these jobs and like giving them processor time. So really quick, the average or the area of these rectangles is just, well, the height of all these is 1. So I think it's a strange question. Is just how much time do all of these spend? So if we look at it here, maybe we'll just draw a table. Arrive, end, and then number. So we have, we'll just say the first one is like job 0, and then job 1, job 2, job 3, job 4, and job 5. So the first one arrives at 0, it finishes at 2. Second one arrives at 1, ends at 3. 1.5, 3.5, 3.25, 4.25, 5.25, 8.25, 7.75, and 8.75. So if I want to find out how much time each item was in the system, then all I got to do is take all of these numbers and subtract them by these ones, right? So item 0 is in the system for 2 seconds. Item 1 was in the system for 2 seconds, or 2 time units. I guess seconds is unrealistic. Item 2 was in the system for 2 seconds. Let's throw that at the end. Hopefully that makes sense where I'm getting that from. A minus E. 2, 2, 1, 3, and 1. All right. Is that clear where I'm getting all that from? Makes sense so far? Okay, awesome. So if I wanted to just take the average, I would just take the average of all these, right? So 2 plus 2 plus 2 plus 1 plus 3 plus 1 is 6, 8, 11, right? 6, 8, 11. And then we had a total of 6 items. That's about 2. That's like, probably like 1.8, something along those lines. Actually, I guess 1.16 times 5. Yeah, 1.8, about. In fact, maybe exactly. And so that's the average time that it's in the system. So that's W. So that's part of Little's Law. And then we want to figure out the average amount of items coming into the system at a given time. So, I mean, we should be able to just calculate that straight up here, right? Because there's 7.75 seconds, and it gets 6 items over that time. Like, correct me if I'm wrong, but that should be fine for this. Now that one's a little bit less obvious. 1 point... Ooh. I might actually have to pull out a calculator. Uh, 7.75 divided by 6?
It should be 1.29-ish.
Yeah, thank you. Actually, it's got it. 1.29. Cool. And then that's lambda. That's W. That should be how we get that from this. Does that make sense how I got these two, at least? Hopefully. And then, obviously, if we want to find L, then we just got to multiply these two. Where'd you get the 6 again? Sorry. Oh, that's just from the fact that we had 6 jobs. So from 0 to 5. I numbered them. They came from up here. We just had 6 jobs enter the system and then finish. Yeah. So L would be equal to W times lambda, which is just 1.8 times 1.29. Again, why did you divide 7.75 divided by 6? So 7.75 was the amount of time it took for everything to arrive. So the last job arrived at 7.75 time units. And then there were 6 jobs. So I reasoned that would probably be a realistic way to find out how many jobs are arriving per time unit. because we had 7.5 over 6 jobs arriving. Should work out. At least I hope so.
Sorry, dumb question. Why wouldn't we use 8.7?
8.7. Oh, because it's the rate at which they're arriving in the system.
Oh, okay, gotcha.
Yeah. And then we'll just work out this last one. Okay, so that works out to be 2.32. So we get an average of 2.32 items in the system at any given point. Okay. And I'm sure there's a better example in the book. Actually, no, there's not. I looked. They had not a lot on this one. I'm sure you could find some better examples online than I came up with. But now the question is, why do we even do this? What use does it do we have to know that there's an average of 2.3 items in the system? How does that help us with designing a computer? Anybody have any suggestions? So let me pose you this question. What happens if we have one processor and 2.32 items in system? Maybe it has to do with, okay, yeah, somebody got it. Awesome, thank you. Yeah. So if we have one core, I mean, this doesn't really matter. It's just going to sit there and all the jobs are going to have to wait and they're going to finish eventually. But if we had, let's just say, 3 cores, then this program isn't going to have to do any waiting at all, because any of the items in the system can just be thrown into a core while the others are working, and we can parallelize them. So this tells you roughly how many processors you should go with. So 2 would be fine. We would get quite a decent amount of speed up, but 3 we would get it perfectly because it would be able to accommodate that last 0.32 for those couple cases. Does that make sense where I'm getting that from? Or the reasoning? Yeah. Okay, sweet. So that's all I had in terms of textbook problems. Did anybody have any last questions? If not, I guess we'll just end a couple minutes early. When you say parallelize, you mean the ability for the processor to split the core? Yes. Potentially different cores, but it could be also different machines. When I say parallelize, it means to, and sorry, I guess I need to enunciate it more. It's parallelize. Yeah, somebody spelled it out. Thank you. It means the ability to run code at the same time. So that could be on different cores, that could be on different machines. It could be on a bunch of distributed systems, which is how Google's search engine works, is they just have like 1,000 computers all hooked up to each other computing at the same time. Any other questions, I guess? I think we're good. How about reading for the weekend? Reading for the week. Oh yeah, I guess. Yeah, Jorge did mention some readings. I think he has some posted on the website. I skimmed the book. I'm gonna be honest. They're on week 2 readings on Canvas. I mean, week 2 is what we talked about today, so I guess I would suggest reading that. I don't even know what chapter 3 was. Chapter 3, I think it's just like how to hook up things on a motherboard, top level view of computer function and interconnection. I don't know if I'd super recommend chapter 3 unless you're into that kind of stuff. 2.6 to 3.6, it's like hardware stuff. I mean, I guess the whole class is hardware stuff, but it's like, you know, designing hardware stuff. I mean, I just do whatever Dr. Fonseca says.
When are like assignments and stuff? Assignments. I don't see anything. coming anytime soon? Or?
I'm honestly not sure. He'll.
He said. Oh, sorry.
Oh no, you go first.
He was talking that there might be an assignment coming out like the middle of next week.
Oh, okay. Gotcha. He said there's no programming assignments for this? Oh, yeah. Yeah, I think he's going to have you guys do programming assignments. In C++. I think just to understand, like, Amdahl's law. I don't think you're actually going to do any threading or anything. I don't think he's going to have you do any workbook problems, though. But I'm not too sure. Yeah, I thought there was no programming in this class. Me too. There was no programming when I took it. It was just textbook questions. Any other questions? If not, the only other thing is make sure you send me the signed syllabus by the end of the day because I have to put that in the gradebook. Yeah, I don't think the programming assignments are going to be too difficult. I think there'll be things you can knock out in an afternoon. Hopefully. Please. Alright, if nobody has any other questions, I guess you're all free to go. Just remember to send me the syllabus. It doesn't have to be printed. If you just send me an image or like a PDF, then that'll work.
Where should I send it to? What's the best way?
Jorge ideally wanted everybody to send it via Discord, but if you have to email me, that's okay.
Okay.
My Discord is just Sam Black in the thing.
Sam Black?
Yep.
Okay.
Discord DM with it signed. Yeah. Oh, sorry.
Yeah, it's just a Discord DM, right? Like with it signed?
Yeah. Either as an image or a PDF or whatever works for you. If you have to like print it out and scan it, that's okay. Or if you just like write on it with a tablet or a mouse, that's okay too.
Okay, thank you.
No problem. Yeah, use Paint. That's fine. All right. I guess I'll stick around for 5 minutes, but everybody's free to leave.